Welcome to This Explainer. I am so thrilled you're tuning in today because we're about to dive into a truly fascinating, totally invisible world, the world of electrical measurement. I mean, we interact with electricity literally all the time, right? But how do we actually know what's going on inside those wires? Today, we're going to look at the ingenious, highly engineered tools that let us measure the invisible. And spoiler alert, we'll explore why getting it perfectly right is a whole lot harder than you might think. It's a pretty compelling question, isn't it? How do you actually measure something you can't even see? Think about it for a sec. If you have a block of wood, you just, hold up a ruler to it. It's simple. But with electrical forces like voltage and current, you're dealing with invisible, incredibly fast, and honestly, sometimes really dangerous energy. So the challenge here is steep. We have to somehow tap into these forces, translate them into a language we can actually read, and do the whole shebang without accidentally altering the very forces we're trying to measure. To kick things off, let's just get our terms straight. Measurement is officially defined as the act of a quantitative comparison between a predefined standard and an unknown quantity. Sounds a bit formal, sure, but this single concept is the absolute bedrock of all science and engineering. Without proper measurement, there's no tech, no advancement, and definitely no safety. Everything, and I mean absolutely everything, relies on this simple act of comparison.
All right, part one, the anatomy of a measurement.
Okay, let's dive right into this. To understand how we measure the invisible, we really need to look at the architecture of an ideal measuring system first. Just take a look at how this pipeline flows. We start right over on the left with the primary sensing element. This is the part making first contact with whatever we want to measure. But that raw signal, it usually isn't quite enough on its own, so it moves through a variable conversion and manipulation stage, like a transducer or a signal conditioner, which basically translates and boosts the signal while keeping its original nature intact. And finally, that data gets transmitted to the presentation element on the right, which is the display where we actually read the result. It's an incredibly elegant pipeline, really. Moving on to part two, the illusion of perfection. Okay, time for a bit of a reality check. Perfection in measurement, it's an absolute illusion. It literally just doesn't exist. No matter how incredible that pipeline we just looked at is, every single instrument out there has physical limitations that introduce static and dynamic errors. And this brings up an absolutely crucial distinction that we all kind of know but often forget when we're actually working: accuracy versus precision. Have you ever thought your exact measurement might be perfectly precise but completely wrong? Well, accuracy is hitting the true value. It's hitting the bullseye. Precision, on the flip side, is really just consistency. Like, if you have an instrument with a bad zero adjustment, it might give you the exact same wrong number down to the thousandth decimal point every single time. That is highly precise, but terribly inaccurate. So what's actually causing all these inaccuracies? Well, we can break them down into three main villains. First up, we've got gross errors. Basically, these are human blunders, reading the dial wrong or setting the whole thing up incorrectly. It happens to the best of us. Second, systematic errors. Now, these are baked right into the system itself. They can be anything from mechanical friction inside the instrument to environmental factors like a sudden temperature drop to even observer habits like parallax error. And finally, the third villain, random errors. These are those elusive, unknown accumulations of tiny effects that literally require statistical analysis to even figure out. But honestly, the most fascinating systematic error of them all is called the loading effect. I want you to picture this like a detective accidentally altering a crime scene just by walking into the room. When you connect a voltmeter across a high-resistance circuit, the meter itself actually draws a little bit of current. Because it provides a parallel path, the current divides, and the voltage drop you end up reading, it's actually lower than the true reading was before you connected the meter in the first place. So your mere attempts to measure the circuit inherently changes the circuit. Wild, right? Which brings us to part three, the beating heart, the D'Arsonval movement. So with all these wild errors constantly threatening our measurements, engineers really needed a rock-solid core mechanism. Enter the D'Arsonval movement, or if you want to get technical, a permanent magnet moving coil. It's based on a super simple motoring principle. You place a current-carrying coil inside a magnetic field, and it experiences a force that's proportional to the current. I actually like to think of this meter movement as a brilliant but extremely fragile protagonist in our story. It is incredibly sensitive, but because of its super light, delicate winding, it can only handle tiny amounts of current. If you expose this thing to massive electrical forces directly, it's toast. Instant destruction. It literally needs armor. Let's see how they build that armor in part four, taming voltage and current. So the crucial point is, how exactly do engineers adapt this fragile, highly sensitive little heart so it can safely measure massive, powerful voltages out in the real world? Well, looking at this basic DC voltmeter schematic, notice our delicate D'Arsonval movement over on the right. To protect it, engineers add that armor we talked about in the form of a series resistance. This is called a multiplier. The main gig for this multiplier is to limit the current flowing through the basic meter, so it absolutely doesn't exceed its full-scale deflection value. Basically, by knowing the exact resistance of the multiplier, we can safely calculate the massive voltage dropping across the entire circuit without blowing anything up. Let's move on and see how this builds. To make the tool, practically useful, we obviously don't just want one single range. We want a multi-range voltmeter. So engineers simply slap on a multi-position selector switch and a string of standard resistors in series. Just by turning a dial, you can literally select how much armor, how much resistance you need for the specific voltage you're testing. It's a real game changer because it allows one incredibly delicate meter to measure wildly different ranges of power. But wait, what about current? A voltmeter measures potential difference across 2 points, right? But an ammeter, that has to be placed directly right in the flow of the current itself. If we put our fragile little meter right in the path of, say, 50 amps, poof, it would vaporize. So engineers use a parallel resistance called a shunt. This shunt basically acts as a massive bypass highway. It diverts the vast majority of that dangerous current right around the delicate meter coil, letting just a tiny, perfectly proportional trickle go through the movement itself so we can get our reading. And naturally, just like with the voltmeter, we want multi-range ammeters too. But oh man, there is a highly dangerous trap here. If you use just a normal switch to change your current ranges, there's this tiny fraction of a second where the switch is floating between contacts. In that exact moment, the shunt is completely disconnected, and the full, massive force of the current slams right into our unprotected meter. Goodbye, meter. So, what's the clever hack here? A make-before-break switch. This brilliant piece of engineering literally makes contact with the next shunt before it breaks contact with the previous one. It guarantees our fragile beating heart is never, ever left exposed. All right, moving into part 5, adapting to AC and resistance. So, we've successfully tamed direct current, or DC. But there is another massive hurdle waiting for us. Our beating heart, that D'Arsonval movement, it only understands steady, one-directional direct current. So how on earth do we measure alternating current when our meter literally only speaks one-way DC? Well, we have to trick the meter. Now, what's really interesting about the solution is the totally ingenious configuration you see here. The bridge rectifier, made out of 4 silicon diodes. Silicon diodes are absolutely perfect here because they have low reverse current and high forward current ratings. Basically, they act as one-way valves for the electricity, forcefully manipulating those alternating ways before they even get a chance to reach the meter. Let's walk through the brilliant 3-step logic of how this actually works. Step 1, the AC voltage is doing its thing, fluctuating back and forth. Step 2, the bridge rectifier routes the positive wave through normally, but when that negative wave comes along, it flips it. This creates a steady series of purely positive pulses, something we call pulsating DC. And finally, step 3, because the movable coil inside the meter has actual physical inertia, it just can't vibrate fast enough to follow those rapid-fire pulses. So it naturally settles at a steady deflection that is perfectly proportional to the average value of all those pulses. We literally trick the DC meter into displaying an average AC value. How cool is that? Finally, let's look at how we actually measure resistance itself using a series type ohm meter. By popping a small internal battery in there to provide a known voltage and adding an adjustable zero resistance dial to calibrate things, we can figure out an unknown resistance just based on how much current flows through. But what's really amazing about this specific instrument is that its unique dial reads completely backwards. Think about it. Maximum current means there's zero resistance, right? So zero is way over on the far right of the dial. And absolutely no current means infinite resistance, so infinity sits all the way on the far left. It's totally flipped. The sheer amount of problem solving packed into these basic instruments is just staggering when you really look at it. From multipliers acting as literal armor, to shunts bypassing certain danger, to rectifiers flat out tricking the laws of physics. So I want to leave you with this final thought. The next time you look at a crisp, clean digital readout on any tool, ask yourself, are you seeing the absolute perfect truth of the universe, or are you simply looking at a highly engineered, beautifully clever approximation? Thank you so much for exploring this fascinating explainer with me today. Keep learning and always keep asking how things work.